Today on How It's Made. Powder horns. Handcrafted molds. Pierogies. And inner tubes. On the battlegrounds of American history, powder horns were everywhere. These modified cow horns served as carrying cases for gunpowder in 18th century colonial battles and the American Revolution. For soldiers engaged in heated battle, the containers were a good way to keep their powder dry. With the invention of ammunition cartridges in the 19th century, muzzle-loading firearms and powder horns became a thing of the past. But today, they're back. Powder horns are in demand for historical reenactments and among some sportsmen and collectors. The concept of using a cow horn to make a gunpowder container demonstrates the resourcefulness of people in an earlier time. Cow horns were accessible. They're naturally hollow, lightweight, and waterproof. To start, the craftsman selects the cow horn and evaluates it for structural flaws. Finding no cracks or weaknesses in this one, he proceeds. He scrapes off the scale to clean it and get a better look at its condition. Next, he identifies the depth of the cavity with a thin wire. This tells him where the hollow section ends and the horn becomes solid. He marks the spot, then draws another line 1.5 inches down. These markings serve as guides as he now turns the tip of the horn into a spout. He cuts off the pointed end along the second line. He drills into the horn all the way through to the horn cavity. He lays out the design of the spout with rubber rings. He traces around them and then scores the horn at the pencil marks. He files the horn around the score marks to give the spout end the desired contours and builds up a ringed ridge for the powder horn strap to rest against. Next, he gouges the horn to create ornamental notches above the spout. This is known as engrailing. He pencils lettering onto the side of the powder horn. He scratches the horn along the penciled lines to engrave the letters into it. Historically, powder horns were a soldier's canvas upon which he etched maps, designs, and personal information. He rubs ink onto the lettering and it seeps into the fine cuts. When he wipes off the ink, it remains in the engravings to make them really stand out. He slices the other end of the cow horn to create an even edge. Then, he boils butternut holes and wood chips in water to make a dye. He immerses the powder horn in the dye for about an hour to give it a look that would take decades to achieve naturally. It gives the powder horn a yellowed, more aged patina. He now carves a base plug from pine wood. He trims the rough shape to the exact curvature of the horn. He inserts the plug and ensures it's a snug fit. He drills 6 holes into the horn and through to the plug. With a tack hammer, he drives wooden pegs into the holes, securing the plug permanently. He slices off the end of the wood to make it flush to the horn. He stains the wood plug with shoe dye to make it blend in with the color of the horn. Once the stain is dried, he creates a hook for a shoulder strap. He drills holes that are a little smaller than the hook, so that when he pounds it into the holes, the hook is firmly installed. He loops the strap through the hook and stitches it up. He inserts a wooden stopper into the spout, and this powder horn is now ready for containment. But mostly, it will just hang around as a reminder of another time. Mass-produced glass items are typically shaped by automated machines, which insert molten glass into an assembly line of molds. Specialty items are usually cast individually, with the artist manually planting the molten glass in a mold crafted by skilled mold makers. These molds for making specialty glass items are entirely handcrafted. This one, comprised of 3 sections, produces the ornate shade of a glass candle lamp. This one, comprised of 2 sections, produces the lamp's base. The glass manufacturer submits the design sketch of the item to the mold shop. The shop, using computer software, converts the sketch into technical drawings. Then, following the drawings, workers prepare a wooden pattern of the mold. They first make a cardboard template for each mold section. Then trace the template on a piece of wood. Saw along the pencil line. Then finalize the shape with a sander. They send the patterns for the mold sections to a foundry, which casts copies in iron. These iron castings are rough, so when they return from the foundry, the mold makers refine each section with a series of milling machines. This takes a tremendous degree of expertise, as these are not computer-guided automated machines. These skilled tradesmen maneuver the mills manually, following the technical drawings. Once they finalize the shape, they use a drill press to bore holes for the hefty pins, on which the mold sections will pivot open and closed. Iron is the ideal material for glass molds because it withstands a temperature of over 2,000 degrees Fahrenheit for molten glass. Iron does expand with such heat. However, once cool, it contracts and resumes its original shape without any distortion. They mount the mold section on the lathe to begin forming the cavity. Using a tool called a boring bar, a mold maker shapes the cavity as per the technical drawings. Then, he takes the mold section off the lathe and paints the cavity yellow to give him a bright background against which to sketch out the fine details of the design. This particular pattern features circles, which he sketches with compasses. Using an arsenal of chisels with different size and shape tips, he chips the metal to carve out what he sketched. Again, he follows the technical drawings meticulously, giving the carved lines the specified depth and profile. Once he finishes the pattern, he mounts the mold section on one side of a mechanical copying machine called a pantograph. On the other side, he mounts another section of the mold which doesn't yet have the carved pattern. The pantograph stylus traces the pattern on the carved section and simultaneously moves an engraving tool through the identical motions on the uncarved section, transferring the pattern. Because this is a 3-sectioned mold, they make 2 copies on the pantograph. The carving tools leave marks on the surface of the cavity, so the next step is to polish them away with emery paper. On the right, you can see the marks, and on the left, the smooth, polished surface. The sections are now ready to be assembled with pins into a complete mold. When it's time to pour in the molten glass, the pins enable the sections to close and interlock. Once the glass cools and solidifies, the pins make it easier to open the mold to extract the casing. Glass artisans and glass manufacturers alike use handcrafted molds to produce a wide variety of glass items from functional to fancy. The pierogi is a pillowy pastry stuffed with mashed potato or other fillings. Popular for centuries in Eastern Europe, pierogis were initially peasant food. But today, their appeal crosses class and cultural boundaries. And worldwide, there's a growing appetite for pierogis. Pierogis are comfort food, traditionally made from scratch by generations of Polish grandmothers. But today, few people have time for all that work, and the job of making pierogis has moved from the kitchen to the factory. All you have to do is add the sour cream and chives. Production starts with the potato and cheese filling. They boil potatoes until tender. Then, still piping hot, they transfer the potatoes to a mixer grinder. They add a generous amount of shredded cheddar cheese, along with some salt and spices. A spiraling blade mashes and mixes the ingredients. The blade misses a few chunks of potato, so the machine forces the ingredients through a perforated metal plate. It gets rid of the chunks and leaves the mix smooth and creamy. With the filling done, it's over to the dough department. They pour measured amounts of flour into a mixer. They add oil for texture and flavor, and some salt to further enhance the taste. They open an overhead tap, and a measured amount of water flows directly into the mixer. The mixer's roller bars blend and knead the dough to a fairly thick consistency. After leaving the dough to soften a bit, they feed it to a special pierogi making machine. The potato and cheese filling flows into the same machine. It forces both the filling and the dough into a forming device. It's enclosed for safety reasons, so you can't see it here. Inside, the machine shapes the filling into a cylindrical form, and the dough around it into a sleeve. Here, the machine pumps out a roll of potato filling. The dough surrounds it, creating sausage-like form. As the filled dough exits, a roller shapes it into individual pierogis. It also cuts and crimps the edges. This produces uniformly plump pierogis at an incredible speed. This machinery churns out 50,000 pierogis an hour. The freshly formed pierogis ride by a divider mechanism that separates them, preventing clumping as they transfer to another conveyor. An inspector rejects any defective dumplings so that only perfect pierogis head into a freezer. The temperature inside is an icy -50 degrees. It's a winding journey on spiraling tiers where they chill for about 14 minutes. When they exit, they're frozen solid and ready for packaging. The dumplings ride a series of conveyors towards the packaging line. It's a quick journey, giving them no time to thaw. The pierogis funnel into weigh stations. Below, mechanical fingers open bags. The scale releases 22 ounces of pierogis into each bag. That's about 23 pierogies per bag. Hot jaws seal the plastic. The bags of pierogies travel through an X-ray station on their way to the warehouse freezer. It scans them for bits of metal or glass that may have contaminated the pierogies during production. Today, pierogies have many different fillings. There are even fruit-filled ones for dessert. The recipe may be centuries old, but there are few new tricks. The earliest tires were bands of steel fitted to wooden wheels, hardly a comfortable ride. Air-filled inner tubes were part of the first successful car tire in 1911, and inner tubes are still used today in most bicycle tires and many motorcycle tires. These motorcycle inner tubes are made with a combination of synthetic and pure natural rubber. They come in a variety of sizes and offer superior quality because no recycled or reclaimed rubber is used during the manufacturing process. A worker selects a slab of synthetic rubber, a package of chemically enhanced rubber, chemicals used as antioxidants, accelerators, and curing agents, and finally, a package of pure natural rubber. A worker pulls the materials from an internal mixer and guides them into a two-roll mill where they're squeezed together. He trims off the rubber sheet. Ideally, the texture of the rubber sheet is smooth. Carbon black provides pigmentation to the process and reinforces the rubber. The rubber is now sent for cooling. It soaks in a mixture of calcium carbonate, which, once dry, will prevent the rubber from sticking to itself. Workers carefully fold the continuous sheet of rubber in a stack to dry. The next day, the rubber is cool and hard, and the calcium carbonate has dried into a powder. A worker places the small strip coming out of the two-roll mill onto an overhead conveyor belt, which takes it to the next phase of production. The strip falls into an extruding machine, where a turning screw forces the raw rubber through a strainer. A worker uses a wire to cut the rubber strands as they emerge. He places the rubber wad in the two-roll mill once again. The rubber will gradually be shaped in preparation for the next phase of extrusion. Squeezed into a strip, the rubber falls into a tube extruder machine. As it passes through the die, it emerges in a cylindrical shape. The rubber tube is hot. Water cools it down and cleans away any remaining residue. The rubber tube now enters a cutting machine. Calcium carbonate powder helps prevent sticking. After being cut, a hole is punched in the tube and a valve inserted. The first cone punches the hole. The second inserts the valve. A worker replaces each valve after it's been inserted into the rubber tube. This machine can process 22 tubes per minute. Here is the rubber tube with the hole punched and with the incomplete valve inserted. A worker now connects the two ends of the cut tube. He places both ends into the machine, which, using different steps, cuts and fuses them together. By the time the machine completes the process, the worker has two more loose ends in place. First, the knife cuts both ends of the tube. By clearing away the calcium carbonate powder, the two heated ends can stick together. No glue is needed. The cut is clean and straight. Heat, combined with the rubber's natural stickiness, firmly holds the seam together. A worker now pumps air into the circular tube. He hammers wax into the incomplete valve in order to temporarily seal the air inside. Another worker places the tube in a mold. It will be heated for a few minutes, part of the vulcanization process. The wax that held the air inside has melted, but after being vulcanized in the mold, the tube retains its cylindrical shape. To flatten the shaped tube, any air remaining inside is removed using a vacuum. These workers give the inner tube its finishing touches. They complete the valve by adding a core, followed by a ring, a nut, and a valve cap. They fold the finished inner tube and circle it with 2 elastic bands. The folded inner tubes are inserted in packaging that is then heat sealed. Ready to hit the open road, these motorcycle inner tubes are sure to get riders pumped.